Just tomorrow's lab is going to be experiment 7, Charles' Law. And so what you should do is just read through this. It doesn't take very long to skim through it. Charles' Law is a law that we're going to talk about today. For Charles' Law, we're going to be dealing with hot and cold water and air. And so you'll need your safety goggles for tomorrow, just in case, boiling water, we don't want that to get into our eyes. Also, you'll need proper footwear. So you don't want to spill boiling water on bare feet. Well, Charles' Law is something we're going to talk about today in class. Charles' Law deals with gases, so let's take a look at that. Where did we leave off last time?
Are we going to finish the last lab? Because we didn't finish last time.
Yeah, we'll finish.
So we'll do that first and then this?
Yeah, right.
Oh.
We're going to do it. So we can do both first. Charles' Law, we're just going to do two data points. What else did we talk about yesterday? Is this where we left off? Yeah. Talking about pressure, gas pressure. The difference between gas and liquid pressure here. If you think about liquid pressure, the bottom of this is going to have the highest pressure because you got all this weight, the weight of the liquid pushing down on here. And one way of thinking about pressure is it's the weight. It's the weight of the liquid. In this case, it's going to weigh less up here than down here, and then some intermediate values here. And when we look at the weight of the gas, in this case, the weight of the gas is generated by the collisions of the particles with the container. So since the collisions are pretty uniform throughout the entire volume of the container, the pressure is uniform throughout the entire volume of the container. Whereas liquid pressure is, it's not. You can have more liquid weight down here than up here. We talked about kinetic molecular theory here. Excuse me, did I mention that the particles aren't really sticky, and so they collide without sticking to the walls, and they collide without sticking to each other. Otherwise, the force of the collisions would decrease, droplets would form. So these particles are moving around. So this is what the attractive forces of the stickiness. So the attractive forces are negligible. And so they just are colliding with each other in the container. Also this last one, molecules interact with one another and with the container walls without loss of total kinetic energy. And so what they're also saying is they don't slow down. If they stick a little bit to the walls, you would think it's going to slow their speed down, but it really doesn't. As long as the attractive force is negligible. Here. So these are just going to glide, bounce off, so without losing much speed. Another part of kinetic molecular theory, and that is gases consist mostly of occupied space or empty space. Empty space here. The A liquid like this is mostly occupied space. There's little spaces between the molecules, but not much. The molecules are pretty much touching each other in liquid. So you're going to see gases are mostly empty space. So this is a snapshot. Did I talk about this already? No. So if we take a snapshot, yeah, nothing there, just empty space, then the gas part of the molecule there. Gases are going to have a much lower density. Over here, the space is much more densely packed. In fact, gases have a density of about, what, 1,000 times less, 1,000,000 times less, 1,000,000,000 times less than the liquid. Yeah, about 1,000. And so if we look at the force, one way of thinking about the pressure is it's the weight. Another way of thinking about the pressure is the force. The force of what? It's the force of the collisions with the wall. And so when we're looking at the wall, it's we take a unit area, so a small section of the wall, and see how much force is generated by the collisions of gas particles with the wall. So the force of collisions of the gas particles with the wall of the container. When we look at the collisions, certain things can change that, and that is volume. If you make a small volume, then the gas particles are going to be more crowded, there are going to be more collisions, versus a big volume, it will be less crowded. And the amount of gas, if you force a lot of gas into the volume, more collisions, more pressure. Very little gas, not much. And then the temperature. The temperature is going to change the speed. And so at higher temperatures, the particles are moving faster and they're going to have more forceful collisions, which generates higher pressures at higher temperatures. Lower temperatures are going to have lower pressures. The particles are moving slower. So there's a lot of writing on this slide. So how do we measure the pressure of a gas? There are lots of instruments that you can use to measure the pressure. So there are gauges you can attach to a container like that. And some of these gauges, they have different ways they operate. Some gauges operate by spring in a diaphragm. Other gauges operate just by a diaphragm in there. And so as the pressure goes up, the gauge changes. This is a mechanical pressure gauge that uses a spring diaphragm. There are other pressure gauges out there too. One pressure gauge that I used to use a lot was this. If a gas is mostly empty space here, then one way you can measure pressure is I was doing stuff at pretty high vacuum. And so to measure the pressure here, I would use a pressure gauge that relied on temperature and what they call thermal conductivity of the medium. Do you know vacuum thermos? Do you know the whole concept of the vacuum thermos? Well, vacuum thermoses are very nice because they're really well insulated. So what is the insulation in a vacuum thermos? Do you know why they insulate? And they can keep hot beverages hot for a long time, cold beverages cold for a long time. And so I have a couple of vacuum thermos mugs. And so what kind of insulation do they use? It must be pretty good because it works a lot better than, like, say, styrofoam or some of the other insulated materials. Do you know what the insulation is in a vacuum thermos? It's nothing. So you think, if it's nothing, then if they're not using anything for insulation, then it's got to be cheap, right? Because what kind of insulation? There's no insulation. So you would think it'd be cheap, but it's expensive. Why is it so expensive? A real vacuum thermos. There are a lot of thermoses that have a double wall construction. This is double wall construction. There's an inside wall and an outside wall. And between the inside and the outside wall, you want some sort of insulation. Their insulation is nothing. here. In fact, if they could have absolutely nothing in between the inside wall and the outside wall, then your hot beverage would never get cold. It'd stay hot pretty much forever. Why?
Because he tries to travel to places that are cold.
Yeah, he tries to travel to places that are cold, but the situation is this. Like, if you touch a hot object, heat's going to travel. How does it travel? The hot object, the atoms are moving very fast. And the cold object, your finger, the atoms are moving slow. And so if you touch the hot object, what's going to happen is there's going to be heat transfer. That is, some of the kinetic energy from the hot object is going to be transferred to the cold object, your fingers, the cells, the atoms, whatever, in your fingers. And your fingers are going to go up in kinetic energy. So the cold object gets hot, the hot object gets cold. That's heat transfer. Excuse me. But if there's nothing here, then you have all this kinetic energy. It can't be transferred because there's nothing to transfer to. You know, nothing to rub that heat off onto, right? And so what's the object? There's no object. If there's no object, then it's not going to get hot.
Let's say you drop it and you dent it. That would affect the.
That shouldn't affect it. It should still work. We've as long as you don't break the vacuum. If you break the vacuum, then it's worthless. Because if you break the vacuum here, you know what a perfect vacuum is. A perfect vacuum is what? Nothing, right? A perfect vacuum is nothing. It's empty space, real empty space. So the problem is if you dent it and you break the seal, or the seal breaks, then air leaks in. If air leaks in here, then all of a sudden you can have heat transfer. You know, what's going to happen is this hot is going to warm up the air, which is going to warm up the outside, and then heat's going to dissipate out, and so your hot beverage is going to be cold. Or heat can get in. You know, it's hot out here, so kinetic energy is transferred to the outer wall. But if you have a perfect vacuum here, then that kinetic energy is not transferred over here. And so if they could make a vacuum thermos like this with a perfect vacuum in there, then your hot beverages would stay hot forever and your cold beverages would stay cold forever. But they can't make a perfect vacuum. How hard is it to make a perfect vacuum? Really hard, you know. And not only that, is this thick enough? How thick should you have your mug? You know, how thick should the walls be to have a decent vacuum? Let's say an ultra-high vacuum. If you want an ultra-high vacuum here, and it would stay hot for a very long time, how thick are the walls on an ultra-high vacuum setup? Like 4 inches thick, or 3 inches, or 1 inch thick. You know, it would be huge. And so, anyway, there's contact up here, so there's going to be some heat dissipation. So heat can be transferred up here, which is in contact with the outer, but it'll slow it down if there's a vacuum in here. And so, so the vacuum pressure gauge works like this, you know. The vacuum pressure gauge works like this. There's a hot probe and a cold probe. And it just measures the temperature difference between the hot probe and the cold probe. You know, if there's a lot of gas in here, then a lot of heat can be transferred from between the hot probe and the cold probe. If there's very little gas, then it's going to take a long time for the cold probe to warm up. And so that's the type of gauge I use to use. But there are a lot of others. There are 2 types of gauges, or 2 types of pressure measuring devices that are discussed in this chapter. Those 2 types are the barometer and the manometer. Both of them, the barometer and the manometer, measure pressure in the same way. You know, it's not measuring by thermal conductivity. It's measuring it by a balance. You know, like you guys used the triple beam balance in lab last week. It weighs it like that. And so, and the only difference between a barometer and a manometer is barometers are used to measure the room pressure. or the outside pressure. And so barometers are made to measure what we call barometric pressure, the pressure generated by the atmosphere, the air, or room pressure. So barometric or atmospheric pressure. However, manometers are made to measure the pressure of a gas sample. So, they both operate in the same way. You know how much a gallon of water weighs, Bob? Did we do that calculation?
It's 128 ounces, right?
Yeah, a gallon's 128 ounces. How many pounds does a gallon of water weigh?
8.
Yeah, 8 pounds. 8 pounds. How many pounds does a gallon of air weigh? It'd be about 1,000 pounds. I mean, not 1,000 pounds. It'd be 1,000 times less, right? Because gases have a density of about 1,000 times, roughly. And so, if you have 8 pounds of water, that would be about a gallon. If you have 8 pounds of air, that would be about 1,000 gallons. 1,000 gallons should be 8 pounds of air, so pounds of air, 1,000 gallons. Well, how many gallons of air are there in the atmosphere? Oh, yeah, a huge number, right? And so, although it doesn't feel like much, there are a lot of pounds of air. And you don't feel it because we're used to it, but if we weren't used to it, you would feel it. So, for example, for every square inch of our body, do you know how many pounds of air is pushing down on it? About 15 pounds per square inch. And so the atmosphere weighs that much. I mean, it's a pretty heavy blanket. And so the balance is going to be like this. On one end, we're going to have air, or atmospheric pressure. So we call it atmospheric, which is the same thing as barometric pressure. Use a barometer. So I'll just abbreviate BAR, barometric pressure. And this is going to be about, let's say about 15 pounds per square inch. Here. And that's because there are many, many gallons of air in the atmosphere, and we can fill it. It weighs a certain amount. And so on one side you have 15 pounds. And then on the other side we need, in order to balance it, we're going to need how many pounds? We're going to need 15 pounds to balance that out. And so if we put 15 pounds on the right, we'll put 15 pounds on the left, and the balance is balanced. And so what we could do is we could use those little masses that they have, for the balance, and just put solid masses there. But we aren't going to use a solid mass, and there's a reason for that. Due to the construction. In fact, we're going to use a liquid. If we use a liquid, this, I'm going to have a square inch here. As far as liquid goes, maybe I'll use water. If I use water here, how much water would I need to get 15 pounds per square inch, roughly? These are just rough numbers. We'll come up with a more precise calculation. But do you know about how much? Well, that would be, let's see, a gallon weighs about 8 pounds, so I'd need about 2 gallons worth, right? 2 gallons worth on a square inch. Well, it turns out the height of this would be the area times height. I'm going to get the pressure or the weight of the water. This is the pressure of the H2O liquid equal 15 pounds. Pressure is force, and force we can think of as weight, because weight is just force and mass. And so to get that 15 pounds, I'm going to need about 30 feet of water. 30 feet of water. Well, I know that air, you know, the density of air changes with elevation. But if air is about 1,000 times less, then if I need about 30 feet of water, how many feet of air do I need to be at the same weight? I need about 30,000 feet of air. So I'll do that. I'll get about 30,000 feet of air. Would be the height. So the height times the area gives us the volume thing. And so, in other words, to get 30,000 feet of air would weigh the same amount as about 30 feet of water. Well, water is not the most dense liquid. What is the most dense liquid you can think of? Syrup is much more dense than water, yeah. So that syrup, is it pure or a mixture? It's a mixture, and so it depends on who mixes up the syrup. That's going to vary the density or where the syrup comes from. Mercury. Mercury is the most dense liquid. And it turns out that if instead I use mercury, I don't need as much to balance it out, because 30 feet of water is pretty huge. You know, that's like 3 or 4 stories up. That's actually more than 30 feet. And so if instead I use mercury, I can use a lot less mercury to balance it out, because mercury is really dense. In fact, mercury is more dense than lead or less dense than lead. Do you know what lead is? Mercury is let's look at some numbers here. Do this. Goes back to chapter 3. So mercury is 13.6, lead is 11.4. Is mercury more dense than lead or less dense? More dense. You know what that means? That means that will lead float on mercury or will lead sink? Lead would float. So you'd have to force the lead to sink. Not easy. How about gold? Would gold sink or would gold float on mercury? Gold would sink. So lead is dense, you know, very dense, but mercury is even denser. And so what that means is maybe we don't need as much mercury. You know, 15 pounds of water is like 30 feet. 15 pounds of liquid mercury would only be, well, it turns out that it's only like 3 feet, less than 3 feet. And so if I use mercury, liquid mercury here, then I'm going to do this in millimeters. We'll go, it's only 760 millimeters of mercury. So 760 millimeters of mercury would weigh like 15 pounds versus 30,000 feet of air. Both of them weigh 15 pounds. 30,000 feet of air, about 3/4 of a meter of mercury. They weigh the same, so it's all balanced out. And so this is how a barometer works. The barometer is going to work by balancing the two weights. And so when we look at the barometer, this is the balance here. On the outside here, I have the weight of the air. So I got 30,000 feet of air on the outside. On the inside of this tube, I just have mercury. There's no air in here, just mercury. And so I want the two to weigh the same. If they weigh the same, then they're at the same pressure. So 30,000 feet of air, 760 millimeters of mercury, and that's about 15 pounds. 15 pounds of air, 15 pounds of mercury. Now, what happens if the air pressure increases? If the air pressure increases, then that's going to tilt this. If this tilts it, the mercury is going to rise up. And so as the air pressure increases, the mercury level increases. As the air pressure decreases, the mercury level would drop. And so the height of this mercury column is directly proportional to the weight of it, right? The higher the column is, the more it weighs. The lower the column is, the less it weighs. The weight is proportional to the force on that. And pressure is force per area. And so in other words, this. What we can do is we can just recognize that the height of this is directly proportional to pressure. And so the height of the water is directly proportional to the pressure of the water. The height of the air is directly proportional to the pressure. This is very approximate because, you know, the air gets thinner and thinner as you get up in elevation, so the density changes as you go up. And so the way we measure it is, rather than converting the height into a weight and all that other stuff, what we do is we just base it on the height of the mercury. And so what we say is this: 760 millimeters of mercury is equivalent to the air pressure, the pressure of the atmosphere. And that is just the average, you know. What we call the average weight of the air at sea level at the equator. So this is kind of the average. But we're going to define it. 1 atmosphere of pressure is going to be defined as 760 millimeters height of liquid mercury. All right, so we want to know the pressure of the gas. And there are other things we want to know, but let me skip ahead. That's one way to measure the pressure of the gas. The other way is if we use a manometer. There are two types of manometers. There's an open-end manometer and a closed-end manometer. We're only going to look at the open-end manometer. Now, the manometer works exactly the same way as a barometer does, except it looks a little different like this. So manometers are used to measure not the air pressure. Manometers are used to measure the gas pressure. Air pressure meaning, you know, atmospheric pressure. And so it does it in the same kind of way. And so let's put a gas sample in here. And then a manometer is very simple. It's just a U-shaped tube, like this, in which one end is open to the atmosphere. And so when we look at this U-shaped tube and we put some liquid mercury in here, there are 3 different scenarios that pop up. Okay, one thing you should notice about liquid mercury is mercury hates glass. Water loves glass. So what water tends to do is it climbs up the sides because it wants to maximize its contact with glass. Mercury hates glass, so it tries to curl up and stay away from the glass. And so water forms a concave meniscus. And we read it from the bottom here. However, mercury forms a convex meniscus. For convex meniscus, from this guy, we read it from the top. So it's just read a little bit differently. Read it from the top here, not the bottom. We get something like this. So in this particular scenario, what's pressing on the left is the weight of the gas. In other words, the pressure of the gas. What's pushing on the right side is the air, 30,000 feet of air, or whatever it is, roughly. So this is the pressure of the air, or atmospheric pressure, or barometric pressure. Actually, those are pretty much used interchangeably. And so the two weights are equal. If the two weights are equal, then it's balanced. It's balanced. Like this. And so the gas pressure is equal to the barometric pressure. So we just read the barometer. It's going to be the pressure of the gas. Like that. The other scenario is this. What if the gas sample weighs more than the atmosphere? Then what's going to happen is balance is going to tilt like this. And we end up with this scenario here. So if the gas is under higher pressure than the atmosphere, then that's going to cause the levels to move. So this level is going to go down here. This level will go up. This is liquid mercury. We use liquid mercury. Why do you think we use mercury, even though it's so toxic? We use it because yeah, its density, it weighs a lot. We could use water, but it would be huge, huge, unless we're measuring very small. If we're measuring very small pressures, then sometimes water is used. So, the exact same thing, except put water in there. Check that. Okay, what we're going to do is we're going to look at the balance here, and we pick the lower level here. So this is the lower level. Okay, at this point, the balance is balanced. And over here, we have the weight of the gas. Well, over on this side, we have the weight of the atmosphere. The weight of the atmosphere wasn't enough. The weight of the atmosphere is too low. So in this case, the pressure of the gas is less than the pressure of the atmosphere. In other words, the barometric pressure. But if I tack onto that the weight of the mercury here, so then at this level they must weigh the same, otherwise there'd be some movement. And so if I add the weight of the atmosphere plus the weight of the mercury, then they should be equal. How do I get the weight of the mercury? I just measure how many millimeters of height it is. Because the atmosphere I'm going to get in terms of how many millimeters of height of mercury I have from the barometer. And so I'll just measure the height of this from this point here. This point. So that the weight of the gas is equal to the weight of the atmosphere, or the barometer, plus the weight of the mercury. So I use atmosphere and barometer interchangeably here. So if I want to figure out the pressure of the gas, I just need to measure the barometric pressure, and that's where I get atmospheric pressure from, the barometer. And then measure the height difference here. I got to figure out how many millimeters of mercury that is, because the more millimeters, the more it weighs, the fewer millimeters, the less it weighs. And so that's what's happening here. The weight of the gas is greater than the weight of the atmosphere. If you get them equal, I'll draw a line here. This is the equal pressure level. And so the weight of the gas is equal to the weight of the atmosphere plus the weight of the mercury. The weight of the mercury I'm going to get from this height here. Okay, the last scenario is this. Let's say the gas is lower pressure. If the gas is at a lower pressure, then we're going to see something like this, where the levels are imbalanced. And then what I'm going to do is I'm going to look over here. I have the weight of the atmosphere. Over here, I have the weight of the gas. And so from this, we can see that the pressure of the gas is less than the pressure of the atmosphere. In other words, the gas weighs less. But, you know, if I draw this imaginary line here, then at this level, they should have the same weights, you know, because there's no movement. And so if I take the weight of the gas plus the weight of the atmosphere, that would, oh, not weight of the atmosphere, weight of the mercury, then these two should be the same. And so I go, the pressure of the gas plus the pressure generated by this, well, how much mercury do I have? I just measure it in millimeters here. From the top of the meniscus down to that level. And so the weight of the gas plus the weight of the mercury is equal to the atmospheric pressure. In other words, the pressure of the gas here is equal to the pressure of the atmosphere minus the pressure of the mercury. And so here I can calculate what the gas pressure is. So measuring the atmospheric pressure in millimeters of mercury and measuring this liquid mercury pressure in millimeters of mercury. Again, millimeters of mercury would be directly proportional to the pressure. And so that's what we have over here. You can see that the atmosphere weighs more than the gas. And so what we'll do is the atmosphere is equal to the gas pressure plus the liquid mercury pressure. We solve for the gas pressure. The gas pressure is equal to the atmospheric pressure minus the mercury liquid pressure. We use mercury here because mercury is the most dense liquid, even though it's toxic. Otherwise, it becomes too much. Let's say you didn't want to work with mercury. Let's say we wanted to work with a liquid like water instead of mercury. There's no problem. We can use water. I mean, there are certain drawbacks that it has, in addition to not being very dense. But if we use water, it still doesn't mean that people don't use it. People do use water in manometers. However, in barometers, it's a different story. If you use water, you got to be very careful because of this. If I look at mercury, what's the density of mercury? Grams per milliliter. Water has a density of 1.0 grams per milliliter. So in other words, mercury is quite a bit more dense. So if I had a milliliter of mercury, it's 13.6 grams. If I had a milliliter of water, it's 1.0 grams, right? So if I want the same mass, let's say I want this to weigh the same as this, how many blocks of water am I going to need? I'm going to need about 14. In fact, I'm going to need 13.6 blocks of water to equal 1 block of mercury. And so I would need 13.6 of these to equal 1. And so if I make these equal, then a total of 13.6 blocks equals 1 block of mercury. Does that make sense? So let's say the average. What's the average pressure? The pressure fluctuates, you know, day to day. This is why the weather reports, they tell you what the atmospheric pressure is. It's fluctuating a little bit, but the average, or what we call 1 atmosphere, is 760 millimeters. And so if we use mercury in the barometer is like this. So we have the weight of the air, and inside this, we only have mercury, because up here is what's termed a vacuum. What is a vacuum? Empty space. But how did they create that vacuum? How they created that vacuum, they didn't use a vacuum pump for it. There was no empty space there. What they did was they had a full tube of liquid mercury, and they inverted it and placed it in here. So there was never any air in here. So there's a vacuum here. And so what we're doing is we're drawing this imaginary line, and so that the weight inside is equal to the weight outside, as long as there's no movement. So that's the weight of the mercury liquid. And that weight of the mercury liquid on some average day is going to be equivalent to 760 millimeter height here. Well, it's like this. One block is 13.6 blocks. So if I had 760 millimeters of liquid mercury here, what would be the equivalent in terms of liquid water? And so if I have 760 millimeters of mercury, how much water would I need in terms of millimeters of water? And so this, we could use some dimensional analysis for this, here to figure it out. So using some dimensional analysis, 760 millimeters of mercury, and then I need this. For every 1 unit of mercury, so for every 1 millimeter of liquid mercury, I'm going to need how many units of water? I'm going to need 13.6 to give an equivalent. And so for every millimeter of mercury, I'll need 13.6 times that, because water is 13.6 times less dense. It weighs a lot less. And so here, I'm just going to go 760 times 13.6. And so what it means is I need 10,336 millimeters of water, liquid. How many millimeters in a meter? Well, I don't know. And this is what I'm going to do. Millimeters is kind of tricky, so I'm going to go from millimeters to centimeters. How do I go from millimeters to centimeters? Yeah, so this will be, there are 1,000 millimeters per, oh, I don't want, there are 10 millimeters per centimeter. Right. And then I'm going to go to centimeters to inches. So 2.54 centimeters per inch. And then I'm going to go from inches to feet. And so there are 12 inches per foot. And so this is going to be feet of water that I need. So I'll go 10,336 millimeters divided by 10 divided by 2.54 divided by 12. 33.91 feet of H2O liquid. So this goes back to what we were saying earlier. You know, I could use different masses on the left because the mass on the right is always the same. So here's the weight of the air, or the atmosphere. And I need that to equal the weight of whatever I'm using, the counterweight we call it. If I use mercury here, liquid mercury, then I'm going to need 760 millimeters. However, if I decide I don't want to deal with toxic mercury, I want to do this with water, how many feet of water is that? than water. And so 760 millimeters of mercury is equivalent to 10,336 millimeters of water, which is equivalent to 33.9 feet. And so I'm going to need about 33.9 feet of water to equal about 30,000 feet of air. And then the two weights are equal. But can you imagine making a barometer more than 34 feet tall? You know, if you put it outside, you know, you'd have to have a spiral staircase to go and measure the height, wouldn't you? Or I guess you could dig a hole in the ground, put it in the ground, and then have the level here, so it goes 3 stories underground. And so this is why mercury, even though it's toxic, mercury is the preferred liquid for doing it. And because of the design, we need a liquid because it's a lot easier to adjust. All right, so we'll do a little concept check here. Let's say you go swimming in a pool. Let's say this is a very deep pool. Let's say you're 33.9 feet underwater. You're 33.9 feet underwater. What pressure do you feel? If you're 33.9 feet underwater, do you know what pressure you feel? You'd feel this. We call 700, what did we call 760 millimeters of mercury? It has a name. We call that 1 atmosphere of pressure. We define it as 1 atmosphere. And so if you're 33.9 feet underwater, you feel 1 atmosphere of water. You feel the weight of 33.9 feet of water above you. And so you're under a pressure of 1 atmosphere. But you're under a pressure of 1 atmosphere of water. And so the pressure of the liquid water is 1 atmosphere. But then again, you have 30,000 feet of air above the water, which is going to generate how much pressure? 1 atmosphere. So you're going to have, you're going to be at a pressure of 2 atmospheres. 1 atmosphere from the weight of the air, plus another atmosphere from the weight of the water, which gives you a total of 2 atmospheres. If you're 10 feet underwater, then you're about 1/3 of an atmosphere underwater. So there'd be about 1 1/3 atmospheres, 10 feet underwater. Can you feel the pressure? You know, the extra third of an atmosphere? Yeah, if you're 10 feet underwater, you feel it. This is not really correct, because if we had a huge container, then the top of this huge container would be at lower pressure. The huge container, let's say, extends from sea level to the top of Everest. You know, the air pressure at the top of Everest is lower. It's because, you know, less gas. That's way less. But there are no huge containers like that, except for the atmosphere. The atmosphere, we look at differently to this. So gas samples can be uniform here. We aren't going to be able to measure the difference in pressure between the top and the bottom of this. For sure, for liquid, we can. And so that's pressure. But there are other things we like to measure for gases. The other things we like to measure for gases our volume. What's the volume? Here, the temperature and the amount. The amount of gas, we'll talk about later, but the amount of gas is important. So let's say you go out and buy a tank, a 5-gallon tank of helium. So you go out and buy a 5-gallon tank of helium, are you always going to get the same amount of helium? You know, fixed by, no, because it depends on the pressure and temperature. You know, you could go out and buy a 5-gallon tank of helium and it's empty. You know, when you try to fill up to the balloon, nothing happens. Or it could be full. And you can tell by the weight of the tank. The weight of the tank is going to tell you if it's full or empty. And that weight of the tank is the amount of gas that's actually present in there. And so when we buy gases by the mass. And so if I want to buy helium, I'm going to buy 2,000 grams of helium. If I buy 2,000 grams, then I know how much I'm getting, regardless of the volume, pressure, or temperature. Because will 2,000 grams change with temperature? Let's say on a cold day, I'm going to have more than 2,000? No, the 2,000 grams is 2,000 grams. So it doesn't change with volume, it doesn't change with temperature, it doesn't change with pressure. So the amount. We'll talk more about the amount later. But in relation to, you know, pressure, the smaller the volume, the higher the pressure. The bigger the volume, the lower the pressure. Temperature, the higher the temperature, the higher the pressure. The volume is inversely proportional. Smaller volumes lead to higher pressure. Temperature is directly proportional. Higher temperatures lead to higher pressure. The amount is directly proportional as well. The more crowded it is, the more collisions you're going to have. So I talked about the atmosphere. Unit of pressure based on atmospheric pressure at sea level and capable of supporting a mercury column 760 millimeters high. So one atmosphere is actually defined as 760 millimeters mercury. This is exact. Because the pressure does fluctuate day to day. So if you just take the average, this is it. There are other ways of saying millimeter of mercury. Millimeter of mercury is kind of long, so some people say torr instead. Torr is the same thing as 1 millimeter of mercury. And so this is 760 millimeters of mercury, which is the same thing as 760 torr. Torr is named after Torricelli, the inventor of the barometer. This is the SI unit, Pascal. The SI unit comes from physics. And so this is a definition based on kilogram and gravity and all that kind of stuff. This is Pascal. It turns out 1 atmosphere is equivalent to 101,325 pascals exactly. This is exact. The Pascal. We'll talk about the bar. You know, the bar is what metric using countries represent pressure as. We use atmosphere. We use millimeters of mercury. Except the news. The news uses inches of mercury. And so as far as inches of mercury goes, this is the conversion. 760 millimeters of mercury is equivalent to how many inches of mercury? This one I don't memorize. I don't bother memorizing this one for 2 reasons. One, is this exact? No, this is approximate. And 2, it's so easy to derive because it's just a simple dimensional analysis problem. We have 760 millimeters of mercury, and then what do we do here? We get rid of, well, in dimensional analysis, we'll try to get rid of millimeters of mercury liquid, but is there something that converts it? No. And so we look at the next best thing, millimeters. Is there a way to get rid of millimeters? Yeah, we can go from millimeters to centimeters. And then from centimeters to inches. And so let's get this to more digits because 760 is exact, right? Is this exact? This is exact. This is exact. So we could use as many sig figs as we want. because all of them are exact. The only reason we're going to stop is because I don't want to write that many sig figs. So 760 divided by 10 divided by 2.54. So all these are allowed in your calculator, 29.9212598.4, dot, dot, dot. If you had a better calculator, you get more digits. The calculator is going to round. Most calculators carry 8 to 10 digits, maybe more, maybe less. This will round. Inches, which will shorten to 29.92 inches. This is to 4 sig figs. But we're not constrained to 4 sig figs. We can use as many as we want because everything's exact. So on the news, you'll hear the pressure in inches in the U.S. Also, turns out you could hear it in PSI as well. 1 atmosphere is equivalent to 14.70 PSI. Pounds per square inch. I said 15 pounds. But really it's 14.7 pounds. I just rounded it to 15 to make it a little easier. But if you need better accuracy and precision, then use 14.70. Okay. Now, if you're in a metric country, they don't use atmospheres. They don't use millimeters of mercury or inches of mercury. You know what they use? Bar. And so bar is the SI unit of pressure. And so it turns out that 1 atmosphere is equal to 101,325 pascals, which is equal to 1.01325 bar. And so that's where that 1 bar is equal to 100 kilopascals comes from. Because what we want to do is we just want to move the decimal place 5 over. And so 1 atmosphere is 1.01 bar. And so when you look at the atmosphere and the bar are very similar. They're very close to one another here. The atmosphere and the bar. And so what we hear is we hear either atmospheres or millimeters of mercury. What they hear is bar or millibar. Millibar. And so as far as millibar goes, this would be how many millibar? This is 1.01325 bar. How many millibar is that? That would be 1,013.25 millibar. And so a millibar is used instead of a millimeter of mercury or instead of a torr, to give fine measurements of the pressure. We can use bar is interchangeable with atmospheres, and millibar is interchangeable with millimeters of mercury. All right, so let's do some unit conversion. Try this one. The pressure, actually, we'll take a break now. It's 3 o'clock. So we'll try this one after the break. We'll go for a break for 10 minutes.